So we talked about alpha decay in a previous lesson, and I'll put a link to the video in the card at the top here or in the comment section below. But today we're going to talk about beta decay, and beta decay comes in two forms. So let's say this is our parent nuclide, and this nucleus here will contain a number of protons and neutrons. Now, if this nucleus undergoes beta decay, it will either eject an electron from the nucleus along with an anti-neutrino, or it will eject a positron, which is the antiparticle equivalent of an electron, or an anti-electron, along with a neutrino. So this is an anti-neutrino, and this is a neutrino. And we also have some kind of energy from this process. So the difference between an electron and its antimatter equivalent, the positron, is the charge. So an electron has a charge of 1.60 times 10 to the minus 19 coulombs, negative, but a positron has exactly the same charge, but a positive 1.60 times 10 to the minus 19 coulombs. They have the same mass, and all other properties of the positron and the electron are the same except the charge. So we can either have beta decay where we're emitting an electron and an antineutrino, or the parent nuclide is emitting a positron and a matter neutrino with some energy. And sometimes you'll see the electron from beta decay written like this, beta negative, and the positron beta positive. So when beta decay occurs, the parent nuclide undergoes certain changes depending on the type of beta decay. So let's say, first of all, we focus on beta negative decay. This is where an electron gets ejected from the nucleus and an anti-neutrino with some energy. When this happens, a neutron in the parent nucleus gets converted into a proton. So if we have a single neutron in the parent nucleus somewhere, it transforms into a proton, and through this process, an electron gets ejected, and we can write it like this, with an anti-neutrino plus energy. So the mass number of the parent nucleus doesn't change. So the total number of neutrons plus protons in this nucleus here stays the same. The only change that occurs is a neutron gets converted into a proton, and this is beta negative decay. If we have another parent nuclide here that is undergoing beta positive decay, then we have a proton in the nucleus somewhere here getting converted into a neutron, and a positron is ejected from this nucleus. And we can write this like this. And we also get a neutrino being ejected at the same time, plus some energy. So this is a positive electron, and that's a normal electron. Now, quite often, this positron here, this positive electron, when it gets ejected from the parent nucleus, it very quickly comes into contact with an electron. An anti-electron or positron coming into contact with an electron will cause them both to annihilate, and this will release gamma radiation. So let's say we have this nuclear equation. We have a phosphorus atom with a mass number of 30 and a proton number of 15. So we have 15 protons in the phosphorus nucleus and a total of 30 neutrons plus protons in the nucleus. This undergoes beta-positive decay. What element do we end up with after this decay? And what gets ejected from the nucleus? So beta-positive decay always occurs when a proton within the parent nuclide gets converted into a neutron. So we're losing a proton from the phosphorus nucleus here. So we got a proton being converted into a neutron, and we get a positron or beta positive particle ejected plus a neutrino. Also notice here that our mass number doesn't change because we're not losing any nucleons in this process. We're simply converting a proton into a neutron for beta positive decay. So we can fill in the mass number for our element here. So that remains at 30. But what is our proton number after the decay takes place? So we're losing a proton, which means that our 15 here turns into 14. So our new element has a proton number of 14 and a mass number of 30. Now, if we have a periodic table, we can see what element this is. So we've got phosphorus here with a proton number of 15. A proton has been transformed into a neutron, which means now we've got 14 protons. So our element has changed from phosphorus to silicon. So we can update this to silicon. And we already know that this is a beta positive decay. In other words, we're ejecting a positive electron or a positron. So this question mark turns into a positron. And when we've got an antimatter particle in this section here, we always have a matter neutrino. So what if we have a lead nucleus with a mass number of 214 and a proton number of 82, and this undergoes beta negative decay? What type of element do we end up with? And what gets ejected from this lead nucleus? So when we have beta negative decay, a neutron in the parent nuclide gets converted into a proton. So we've got a neutron here, that gets converted into a proton, and we're ejecting an electron, which we can also write like this, plus an anti-neutrino. So what does that mean for the lead nucleus? If we've got one of the neutrons in this nucleus here being converted into a proton, well, effectively, we're adding a proton to this nucleus, but the mass number stays the same because we're simply transforming a neutron into a proton. So we got the same mass number of 214. We're adding a proton now, so 82 becomes 83. So if we have a look at our periodic table, we can find out what element we end up with when lead undergoes beta negative decay. So what do we get? So here's lead with a proton number of 82. The proton number increases by 1 to 83. So we get bismuth. So we got bismuth here. During this process, we're ejecting an electron or beta negative particle, -1, 0 at the top here. And we always have an antineutrino being ejected from the parent nuclide at the same time as the electron. And we write it like this.